This is Jack Jackson. We're going to look at using some combinatorics to solve a classic problem called the birthday problem. So the first thing I want to ask you is how many people must we have in a group to guarantee with probability 1 that at least 2 of them have the same birthday? We're talking about the same month and day, not necessarily the same year. How many would that be? Well, since there are 366 different days of the year, we're guaranteed at least one repeat when we get to 367 people. This is an example of what's called the Pigeonhole Principle. If we select k objects from n objects where k is greater than n, then there has to be at least one repeat. Okay, so we know it takes 367 to guarantee a repeat. So if we have a group of n people, what's the probability that at least 2 of them will have the same birthday, month and day, not necessarily the same year? At what point would that become a good bet? So would you bet me if we had a group of 40 randomly selected people that, if I bet that they have the same birthday, would you take that bet? Would you take it at 30, 20? Interesting question. Well, it turns out that this has a somewhat counterintuitive answer. And we're going to simplify this slightly. So suppose there are 365 equally likely days in the year for birthdays. And it's a simplification because some years have 366, 1 out of every 4 have an extra day. And in reality, not every day is equally likely. There are some slight variations in probability of a birth from day to day. But the probabilities we compute here will vary very little from the actual situation in reality. So at least this will be a pretty good approximation. So here's one way we can think of it. Think of the sample space of possible birthdays. There are 365 possibilities for each of the n people. So there are 365 to the nth power equally possible arrangements, possible elements in the sample space. Notice that the order matters and repetitions are allowed. So what we're going to do is first figure the complement of the event. Suppose that there are no birthdays in common. Then there are 365 choices for the first birthday. For each of these, there are 364 choices for the second, 363 for the third, and so forth. And this results in 365 permute n different choices of birthdays where the order matters and no repeats are allowed. So the probability that all the birthdays are different is 365 permute n divided by 365 to the nth power. And this is definitely an example where finding the complementary probability is a lot easier. See, if you think about making a probability tree with this, there's only one branch where they're all different. One way to do it where they're all different is where you get no repeats. So this is easier to count this way. And so then we do 1 minus that, then we get the probability that at least 2 of them have the same birthday. So if we do 1 minus 365 permute n divided by 365 to the nth, we would get that probability. If we suppose there are 366 days a year all equally likely, we could change that just slightly by changing that to 366. And the probability would be pretty close either way. So I've done it out. I've worked it out in Excel with this particular formula right here, and this is the numbers that we get. Of course, if you only have one person, there's no probability of a duplicate. 2 people, it's still a very small probability, 0.0027, and so forth. But it actually goes up fairly quickly. And notice by the time you get up to 20 people, you're already up at over 40%, and it actually reaches over 50% at only 23 people. So it's a little bit better chance, just barely better chance of getting the same birthday with 23 people than it's not, or it's about the same. And notice if you're talking about 30 people, that's a 70%. Almost 71% chance that there will be 2 of them with the same birthday. And at 40, which is what I mentioned first, I think a while ago, 40, it's a really good bet, over 89% chance that they're going to have 2 people with the same birthday in a group of 40 people. So if you had 40 people, that's a really good bet. 30 people, it's still not as good a bet, but still the odds are definitely in your favor there. About 23 people, it could go either way, about equally likely, and less than that, then it's more chance that there's not a repeat. But that's a lot less than you might think, perhaps. That only takes like 24 people to get the probability, 23, 24, to get above a half for the probability, and yet it takes 367 people to guarantee a duplication. So that's the birthday problem.